Start my timer so I don't run over. Can you hear me? Is this thing on? Okay. So this is kind of a joke, really. So my name is Russell Brown. I'm a software engineer. I work for a company called Basho, who are sponsoring tonight. So thanks, Uncle Basho, for the beer. Who here is a software engineer? I'm trying to imagine the intersection of the audience for the last talk and this talk. So you're a software engineer, you're a developer, you're a programmer, you're a dev monkey. You type characters into a buffer and the computer does what you say. Yeah. All right. So that's good. So it's kind of technical talk, but it's not super technical. It's not really about counting that much either. But that's the kind of framework for the talk. So this is a joke. This is a tweet from Lindsay Cooper, who's a researcher. She's a programming languages researcher. But she also works in distributed systems as well. She gave a talk at one of our distributed systems conferences called Recon. And so this is a tweet I saw, and I was like, that's pretty funny. You know, I retweeted it, and I favorited it. And I had a click. I clicked on it to look at the replies. And the replies sort of came under three broad kind of categories. They were like, haha, good one, Lindsay, that's funny. And there was like, well, actually, Lindsay, I think you'll find. And then there was the third lot, which was like, what? Are you serious? Is this a thing? And I was thinking, well, you know, this time I looked at it, I'm in the first category, but if I'd looked at it a couple of years ago, I'd be in the, is this really a thing? Is counting hard? Are you serious? And so, you know, I think jokes are better explained, usually. So I thought this talk can just explain that joke. So hands up if you got the joke and think it's funny. All right, okay. Hands up if you got it and didn't think it was funny. That doesn't matter. But who's in the group of people who are like, what? Why? Okay, excellent. We're in the right room. So that's a relief. Not full of professors of distributed systems. So here's another tweet from 5 years ago. This is how I got my job. This guy, Dizzy D, Dave Smith, who was the engineering manager at Basho at the time. Brilliant engineer, brilliant engineering manager, just able to enable people to just do their best work. So I answered this tweet with a, please, me. I was a Java developer at the time. Anyone here a Java developer or done any Java development? Yeah, I'm sorry. So I wanted to work in Erlang. Erlang's like a functional programming language. It was really cool. It makes concurrent systems easy to write. And I really wanted to work in it. And I was playing with Erlang at home, but these guys, the guys who wrote React, Basho, they used Erlang daily, and I wanted to use Erlang daily. So So I applied for this job thinking if I can do some Java for them, I can get in by the back door and do some Erlang ultimately. And so when I started working there, the number one feature request for React in 2011, that seems a long time ago, it was counters. People who used React wanted to be able to count things. And I was like, how hard can that be? I'll do this. You know, I'll add counters to React, and then Dave will like me, and the other engineers at Basho will respect me, and I'll get to write Erlang for a living, and life will be good. So, and this is an older meme, but I think it still checks out. Someone in the room will understand this one. So I thought, I'm going to add counters to React. So this isn't what the talk's about. The talk's about why distributed systems counting is hard, and I found out the hard way by doing it. But I'm going to convince you distributed systems counting is hard by hook or by crook. I'm going to start off by talking about this book. Has anyone read this book or seen this book? If you write Java, read this book, go back and look at your code and ask yourself what you were doing. That's what happened to me anyway. This is page 6 of this book. This is chapter 1, introduction. So this is right at the start of the book. If anyone used a database where you use an auto increment field to assign an ID to a record? So this is like a Java class that does something like that. So sorry for being so technical here. We're putting code up on a slide. But here's like a class. It's got a count. It's got a number. That's your value. And this is like you're getting a sequence, you know, get me the next number, get me the next number. And this shows how on a single machine with multiple threads, counting is hard. You can have, the whole purpose of this code is to get a sequence of numbers so that everyone who calls it gets a unique number to identify, like a row in a database, for example. And here we have an interleaving where that doesn't work. So hopefully just by showing you that, you can see that counting on a single machine is hard. So counting on distributed systems is harder. So that's the end of the talk. We can go home. But I thought we might as well look at why it's hard on distributed systems. So before we talk about why it's hard to count on distributed systems, what's a distributed system? So this is Leslie Lamport. He's a distributed systems researcher, part-time comedian. He says that distributed system is one in which the failure of a computer you don't even know existed can render your own computer unusable. And I think we all, everyone who's got one of these understands that, because you carry a computer around in your pocket and every now and again you try and do something and it just can't do anything because you've got no network or some server somewhere isn't responding. But for our purposes, I think this is a better description. What we basically mean is when you've got more than one machine working together, talking over a network to achieve some common task, that's a distributed system. And that's the loose definition I'm going to use for this talk. So anytime you've got multiple machines doing something together, distributed system. So that's what? Now, distributed counting. Why? If it's so hard, why bother? Well, the reason for distributed counters is the same as the reason for any distributed system. So you might have many, many, many updates, which means you need a lot of computing power, more than a single machine can provide, so you have multiple machines. Or you might have many, many counters, many, many things, many items of data, and so you need to have, they won't fit on one machine, so you have multiple machines. So you have a reason for distributed systems. Another reason, a classic reason, is fault tolerance. You have your counters, you're counting something, your network card breaks, you want to keep counting things, have 2 copies of your application, have 3 copies, have 5 copies, have many copies of your application on many machines for fault tolerance reasons. That's a distributed system. You might want to literally distribute your system globally. So for latency reasons, you have a copy of your application in China, one in New York, one in Leeds, and the users use the copy that's closest to them. So another reason for a distributed system, another why. And then this last one I've just added is kind of a bit spurious, but you find that this has become the cause of many distributed systems. People use containers or virtual machines and have this architectural thing of microservices where you have small, compact, separate machines that have a small job, and they talk to each other over the network. So this is a distributed system. So these are all distributed systems. Now, you can't really talk about distributed systems, especially if you're from Basho, without mentioning CAP. Has anyone heard of the CAP theorem or Brewer's conjecture? No one. One. Fantastic. So this always provokes some trouble, because CAP's not that interesting, and it's not really computer science, and safety and liveness are more interesting. But I think CAP's really interesting. CAP's it's a good mnemonic. It's an acronym. It stands for these properties. So it's getting to be a lecture on distributed systems now. These properties of a distributed system: consistency, which is a property of your data. So in the case of our counter, if you update the counter, you then read back the value. So if you add 1, then you read the counter, you get 1. If you add again, you get 2. If you have 2 clients and they're both adding 1 at the same time, after the first add, you get 1. After the second you add, you get 2. That's consistency, just that you see what's occurred immediately. Availability is that if you can contact some node, if you're counting, if you're trying to ask your counting service to add 1, as long as you can reach any node in your distributed system, it will say, yes, I've added 1. It will do the job. And this final property, partition tolerance, is something that you can't avoid with distributed systems, because they live on real-world networks. And on real-world networks, as has been displayed this evening, things go off and they come back on again. Network cards fail, routers drop messages. So you have to have this. So when you have distributed systems, is that there's a fundamental tension or trade-off that CAP describes. This is getting pretty heavy now. So here's a CP system. Here's a system that has consistency and partition tolerance. And to achieve that, it sacrifices availability. This dotted line in the industry stands for a partition. That's where your network can't talk. So we've got 3 copies of our counter up here and a couple of clients trying to add 1. And this might be one of these counters you're using for a sequence. So you absolutely want every single client, when it increments the counter, to get a unique value back. Now, if this node, replica C, can't talk to these 2 nodes, A and B, then the system has to not let it work for one client, for this client over here, client Y. Because there's no way for these nodes to talk to each other and get a consensus on the current value. And so if client X adds 1, the counter is 1. And if client Y adds 1 to an empty replica, its value is 1. And we have 2 non-unique integers. So we're inconsistent. So we've broken our consistency in the face of this partition. So instead, our system goes, well, you know what? I'm just not going to allow you, I'm not going to be available to you over here, client Y, bad luck. You don't get to add 1. So we've traded off availability for consistency here. On the other side, you can trade off consistency for availability. You can choose to let both clients add 1. Now, this is no use for generating unique integer identifiers, but it's fine for something like favorites or likes. You don't want to not serve up a page because you can't increment a counter for the number of hits or something. So in that case, you're available, okay? You don't mind. It doesn't matter if temporarily, when you look at the number of likes on Twitter, it says 5,000 rather than 5,012. You don't care, because eventually it'll be right when everything talks with each other. So that's where you choose availability over consistency. So that's kind of the fundamental trade-off at the heart of all distributed systems, explained through counting. So what do you do as a practitioner, as someone who writes systems, who finds themselves having to count lots and lots of things? Well, you just need to choose the trade-offs that suit your use case. So you decide, why are you counting, or what are you counting? So if you're counting money or votes or something extremely important, or if you're generating unique IDs, if you're counting real-world resources like seats on a plane or rental cars or that kind of thing, or widgets in the warehouse, you need to use a different type of counting. So if you're generating IDs for people or database objects, or a different type of counting, again, for things like likes and hits and favorites, they all have different types of counting because they have different requirements and different consistency requirements and availability requirements. So if you need to have these unique integers, if you need to have this strong consistency, here's a list of systems you can use. If you're a developer and you have to, someone comes to you and says, I need to count something, and you say, what kind of thing are we counting? Well, we're counting money. Okay, well, let's do strong consistency. You can use Zookeeper or Hyperdex, Replicant, React Ensemble, and these all take advantage of these things here, which are protocols designed to give you consistent distributed systems. So Zab, chain replication, Paxos, Raft, ViewStat for replication. And the cost here, of course, is you have, if you're using a compare and swap style thing like React Ensemble does, you have a risk of starvation. There is no global spanning multi-data center strong consistent system out there. Anyone heard of Google Spanner? All right, so there is Google Spanner, but you can't install that and run that, right? So that doesn't really exist. So there's a trade-off here. If you have to have this strong consistent counting, it costs you availability. But you might not. You might think you need strong consistent counting because you're generating unique IDs. But really, there's a way of doing that without having consensus. This is a list of sort of software you can look up on the internet, or search on Google for, and you'll see that you can generate unique ordered IDs without counting, without consensus. So if that's your use case, you don't need to use strongly consistent systems. And again, there's something that's very dear to my heart, which is eventually consistent counting. So there's systems like React and Cassandra, which use these data structures called CRDTs. If you want to talk about those, come and talk to me and I'll talk your ears off. And these have their own trade-offs. You have the idea of drifts or partial failure. So they're accurate, they're eventually consistent. Doesn't mean they're wrong, just means it takes time for operations to propagate for them to be correct. If you want properties like idempotence, you pay more for it by having more state or sacrificing some availability. And there's some work, actually. I'm in a research group for distributed counters, believe it or not. And there's some work, well, it's not just counters, it's all kinds of data types, but counters are the simplest ones. There's some work on being able to add sort of invariants to these eventually consistent counters using something called reservations that we're working on, which, again, if you want to talk about, I will talk your ear off. And then sometimes, perhaps you don't really care exactly how many things you're counting. You just want an estimate. This is even sort of further along the scale from being, this is more available, but it's not as accurate. So the counter I'm mentioning here is called hyperloglog, which is a probabilistic structure. Has anyone heard of this? It's a way of estimating rather than actually counting. So it estimates the cardinality of a set. So if you imagine that you want to count all the visitors to your website, unique visitors, and you do that by storing all their IP addresses in a set, and then you look at the set and you count the IP addresses, and that's all your unique visitors. Well, that's fine unless you're Google or Facebook, and you have billions of IP or millions of IP addresses. That's a very big set, and it's very expensive to read. So rather than doing that, they have these clever mathematical structure, which is a mixture of bit twiddling and bit vectors and maths, which will estimate how many things are in a set. So there are systems that provide this. Redis provides it. React is soon to be providing it. And it's a very small, very compact, and very rapid to update data structure, which will give you a very close estimate to real cardinality. So if the thing you're counting, you don't need an exact number, you need an estimate, this is another option you have, another trade-off you can make. You can trade off some accuracy for speed, performance, and size. So we'll come back to the joke. So does anyone find that funny now? Okay, at least you get it, right? So, oh, there you go. So the joke's been explained. So, counting in distributed systems is fraught with trade-offs because distributed systems are fraught with trade-offs. There's that central trade-off at the core of all of them is the same for counting too. So I've just skipped past the last slide. Oops. But you can still see that. So the thing I want you to take home from this is when it comes to something like counting or comes to using distributed systems in general, is understand your requirements, so that know what you're counting and why in this case, and understand the trade-offs that are available to you, and make them consciously. And the real advice for any engineer who is having to make a system that counts things at scale is use the least consistency or accuracy for your use case, because that gives you the most performance and availability. And I think I've done it so much faster when you're not practicing at home, when you're nervous. So I've got a little bit of time for questions, I think. I'm done.